In this scenario, we are working with cornering. The first thing you want to do, of course, is to put your name in the blank. You can watch this video by clicking here. And then this picture goes with the video that I made with Sarah Scoville and Sean Emberts, and you can get that by clicking down here. The purpose of this activity is to show you that trigonometric and algebraic concepts have real-life applications. Trigonometry is useful in determining the value of the force related to the slope of a curve. The algebraic concepts are related to the friction equation, which is necessary in solving the cornering scenario. So we're going to use the coefficient of friction and trigonometry. We have a ruler, a tape measure, and a level that we use for this experiment. Now, if you notice here, they show going around a curve, and this is high speed or pursuit driving. At the apex of the curve, you're the closest that you can be to the edge of the curve, and then you turn in from the outside and you exit point on the outside also. To understand pursuit driving, though, you need to understand the physics behind the phenomena. Most of these phenomena are based on Newton's laws of motion. The first law is that an object remains in motion at the same speed and direction unless a force changes it. It is also called the law of inertia. So a car slides into the ditch because there was insufficient force to counteract the inertia of the car going forward. The second law states that acceleration is caused by a force and related to the mass. The formula for the second law is force is mass times acceleration. The amount of force is equal to the product of the mass and the acceleration. In a car, the three devices that provide the force are the brake, the gas pedal, and the steering wheel. The three devices can only provide their force because of friction, which is explained in the third law. The third law states that for every action on an object, there is an equal and opposite reaction on another object. If the road and tires have enough friction between them, the force of the brake, gas pedal, or steering wheel can cause the acceleration or deceleration to occur. If there's not enough friction, the force will not be strong enough, and the inertia will cause the car to just keep on going into the ditch. Friction calculations. Friction always opposes motion. It slows objects down, which is why we need to add force to our motion using the gas pedal. Cornering is a complex physical relationship that can be simplified down to the formula at the right. It says that the maximum velocity around a corner is found by taking the square root of the product of the coefficient of friction, which you find on the chart there, gravity, which is 32 feet per second squared, and the radius of the curve in feet. An increase in any of these three would cause the speed to increase, or I guess you would say the speed can increase if any of these three is larger. Static friction is when two surfaces have no relative motion. We could call it contact friction. Kinetic friction is when the surfaces are moving relative to each other. We could call this skidding friction. For our purposes, though, the coefficient of friction will be static if we have ABS, anti-lock brakes, and kinetic if we don't. So, let's do some matching here. Which of these is the first law of motion? Well, that should help you if you read the directions above. Which of these is the second law of motion? Which of these is the third law of motion? Which is the force that opposes motion? Which is the kind of friction when things are moving relative to each other? And which is when they are stationary with each other? All right. So you see a picture here of the corner by ESEC, and if you notice, this picture was taken in 2011 before the intersection was upgraded. The new road has cut down on the number of cars going into the ditch, and the fewer crashes are probably a result of the road being plowed more often and thus raising the coefficient of friction, because if you notice, the coefficient of friction for tires on snow is 0.3, whereas tires on concrete is 1, so it's a much higher coefficient of friction if the road is dry. I suppose the road could be somewhat wet, like 0.6. On a snowy morning, you should still slow down, even if the road is not snowy, but just wet. The fewer crashes, cornering is ideal when you don't move the steering wheel once you start the curve. In other words, the radius stays the same. Because the acceleration going around the curve slows down the car, you can actually press the gas pedal partway through the curve and increase, or at least maintain, the speed that you had at the beginning of the curve. Perform the calculations below to determine the cornering speed. More information on measurements is given in the crash measurements scenario that you see up here at the top under traffic textbook. Next, to convert feet per second to miles per hour, multiply by 15 over 22. So the first one that we're going to do, and if you notice here, we have the formula for Excel, so equals square root the coefficient of friction, so dry road is 1, and ABS, yep, dry road ABS is 1, times 32, because that's the gravity, times 60. Oops, 60. And when we get that answer, we have to multiply by 15 and divide by 22. Okay, so I'm going to copy that formula down here just to make sure that we get the formula for miles per hour correct. All right, now if you have no ABS, notice the coefficient of friction goes down to 0.8. So equals square root the coefficient of friction, 0.8, times gravity, which is 32, times radius is 60 feet. Snow on the road with ABS. Snow on the road is 0.30. So equals square root of 0.30 times 32 times 60 feet. Snow on the road, no ABS. Well, if you notice no ABS, it would be 0.2 is our coefficient of friction. So equals square root 0.2 times 32 times 60. All right, so that's 13.4. So if you notice, the speed that you can go around the curve gradually gets less and less as you go from dry roads to snow. Suppose, though, you didn't stay in your lane. Suppose, though, you went around the curve and got as close as you could to the center, much like you do in the pursuit driving picture that you see here. Well, then the radius is 124 feet. So when you put in the formula square root, it would, it would be dry road is 1 times 32 times, now the radius is 124 feet. Okay, and then for the next one, square root, no ABS is 0.8 is the coefficient of friction times 32 times 124 feet, which is 38 miles an hour. Snow on the road, square root 0.30 if you have ABS times 32 times 124 feet. In every case, gravity is 32. And then finally, if there is snow on the road, and you don't have ABS, your coefficient of friction is 0.2 times 32 times 124 feet. And if you notice, if you have pursuit driving, you can go up to 42 miles an hour around the curve. Well, that's not necessarily exactly correct, because the road is not perfectly level. One of the reasons race cars can go full throttle around corners is that the curves are banked. The picture at the right shows the banked curve at Daytona. The grader at the top is chained to the tar machine so that it doesn't fall down the curve. The formula has many parts, and you see it here on the right-hand side, but you can use your FX calculator to simplify it. The first calculations we're going to make is to find the various angles. Now, if you notice here in the picture, the angle is over here on the left-hand side. The level is 48 inches long. So from the video, we will get the other side of the angle. Okay, so let's look here. And then we want that's going to be the tangent of the angle, is the size from the video divided by 48, or the angle whose tangent is that will be that angle. So to find the formula, we're going to press equals a tangent, which means arc tangent, which is the same as tangent to the -1. And then the size from the angle divided by 48. But this gives us the angle in radians. We also want the angle in degrees. So let's go through them, and let's get the height. So for the first one, the height, if you look at the picture here, is about right at 1 inch. So we would say 1 inch is the height, and the tangent will be 1 inch divided by 48 inches, which is 0.0208. Now we want to know what angle that is, so we would say equals angle whose tangent, so a tan, of this number, and that will be in radians. And if you notice, it comes out almost the exact same, and that's because the angle is so very close to the size of the tangent. If we would want that in degrees, we would take this number times 180 divided by pi, and you type pi as open parentheses, close parentheses, and we would get 1.19 degrees. If we look at the second picture, the angle is 0.5 inches, so we would take 0.5 divided by 48, which, if we want the size in radians, is a tangent of this number, which is 0.0104, again, very close to 0. And our angle is this number times 180 divided by pi. And then for the last picture, the angle is once again 1, so we will have the same numbers as we did the first time. I'm just going to copy them down and put them down here in the picture. So if you notice, angle A is 1 degree, angle B is about a half a degree, and angle C is about 1 degree. Well, what happens if you go into the ditch or don't go into the ditch? Let's wrap it all up to find out how to avoid going into the ditch, either by going slow enough to stay on the road or fast enough to miss the fire hydrant. So we're going to either miss the ditch over here, or we're going to miss the fire hydrant over here. The calculations will include the angle size in theta above. When considering missing the fire hydrant, the angle is negative since the outside of the road is actually curved away. Because of the complexity of the calculations, we will only make 2. The first is the fastest speed to stay out of the ditch if you have snow, and no ABS. The other calculation is the slowest speed to miss the fire hydrant. On both calculations, use the size of the angle in radians if you're using Excel. In the second calculation, angle B is negative. Okay, so what we need to do is to make the calculations, and it involves once again the square root function. So the first thing we're going to do is to put in the square root, but now we're going to deal with the denominator, so we need to open another set of parentheses. 32 is gravity times the radius, which is 65 feet, times, now we've got a sum that we need to put in, sine of our angle, and our angle is angle A, so it's 0.0208. 0.0208 plus our coefficient of friction on snow with no ABS is 0.2 times the cosine of our angle, 0.0208. Let's close out the sum, then we will close out the numerator, and now let's start on the denominator. Cosine of our angle, 0.0208, minus our coefficient of friction, 0.2 times the denominator, or I'm sorry, times the sine of the angle, 0.0208. Rather complicated formula. Now we close out the denominator and finally close out the square root. So we get 21.43, and let's multiply that number times 15 divided by 22, because that's how to convert to miles per hour. Because that formula was kind of complicated, let's pull both of those down into the next box and just make the changes that are necessary. The first one is that the radius increased to 175 feet. But the other thing that you notice here, it says that angle B is negative. So when we do our calculations here, we have to change this number to negative 0.0104 in every case. I'm going to copy that and just paste it into each one of the different locations. If I were changing the coefficient of friction, I would also have to change that. And if you notice, I get 22.2 miles per hour. So the slowest you can go is 14.6. I'm sorry, the fastest you can go is 22.2, and the slowest you can go is 14.6. Ooh, 14.6. And so if you've got all 30 of the points, I guess you're done.